So Doris Kim Sung, Director of Undergraduate Architecture Programs at USC, has one of the most inventive minds in architecture that I know. She's that rare architect who's as comfortable working within the architecture discourse as outside of it, including worlds of engineering, new materials and technology, innovation, and patents and trademarks. She brings active systems to sustainable design far beyond the simple greening of a building, and believes that buildings can breathe and be more sensitive to the changing environment, just like the human skin. And she seeks ways to make the building skin dynamic and responsive. Through grant-funded research, I think she's won every grant in the architecture world and is reaching beyond into other worlds. She's developing smart materials such as thermobimetals to self-ventilate, self-shade, self-structure, self-assemble, and self-propel. Her work juggles between research and teaching at USC. She publishes, lectures, exhibits internationally, and brings her patented inventions to the market. Her TED Talk has reached 1.25 million views, and her work has been awarded Best Product Award most recently by Time Magazine, Architectural Record, Architects Newspaper, National AIA, ACSA, too many to mention. She's been named Fellow Google's Research and Development for the Built Environment, US Artist, and the Rockefeller Foundation, just to name a few. She received her MArch degree from Columbia University and her BA degree from Princeton. And on a personal note, Doris and I have been friends for 36 years. We were two since 1987 when we were students at UCLA, and she is as talented as she is kind and supportive and generous and funny and joyful, and like me, an Angel City Football Club fan. So take it away, Doris.
See, so this is the reason you guys all learn that you have to be good to your friends so that they can introduce you and put you in the best light possible, because I've known Ingelo for so long. And again, from studio times and spending those many hours there, that you all will also know that she also knows the bad parts about it and has conveniently left those out. But anyway.
No
I'm gonna share my screen here. Great. And then I will talk about some of my work. I titled this lecture Architecture Unplugged, and you'll see why as we start to move forward and see some of the projects. I want to talk a little bit about my background, just because you guys are in the journey itself, and so you can get a flavor of where I've been and how I've come here, because again, a lot of it had no plan whatsoever. I never thought I'd be an architect. I never thought I'd be in teaching. I'd never thought I'd be where I am now. And so it's a matter of really trying to think deeply as you go forward in doing whatever you do. And somehow serendipitously, it just, it starts to mold itself. So when I was in college, I actually was a biology major. I was very interested in the math and sciences. Enjoyed doing all that kind of stuff about plants and animals and behavior. I also liked to do the arts, and I wanted to be an art major in college, but my father said absolutely not. You cannot do that. But what I did was I actually took art classes the entire time. So all the way through undergrad and graduate school, I always took art classes just because I enjoyed it so much. Even here, you can see I started to look at freeway systems and diagram them even in etching design, and use them to kind of cross over between what I saw in life as well as artwork. I started to move forward, went to graduate school, started to get really interested. Again, let me back up for a moment. I was going to go to medical school. That was why I was in the sciences. And it was in undergrad that I started to get exposed to architecture and other things. And that's when I decided to change direction and start to look at architecture, because it, in some ways in my mind, was the combination of math, science, and art. There, I started to look at how inanimate objects and inanimate materials can be an extension of the human body. So on the left, you see this prosthetic device. On the right, you see this art project by Rebecca Horn, where it's these long fingers. And you can imagine that using these fingers or these gloves more and more, you become quite good at it, just like chopsticks, and you can actually feel things and sensation through it. And so these are the things that I start to get infatuated with, because architecture too, being made out of inanimate material, should also be that sensitive. So I started to make these objects that try to transfer and understand body movement and material and sensitivity through grad school. And then even after grad school, started to continue to look at the biomorphic, bio-inspired designs. And this actually was one that the eyes would flick open and closed and obviously mimic, you know, eyelids and that kind of movement. I really started to be interested in Maurice Merleau-Ponty's work, The Phenomenology of Perception. Basically in there, he talked a lot about how the experience and absorbing these inanimate objects into your body became part of your body, and that it wasn't through thinking about it in the intellect that did it, but it was through the experiences itself. And he spoke specifically about a blind person's cane, and the fact that through this, you can feel texture, you can feel depth, you can feel all kinds of things coming through the cane, and it becomes absorbed into the body, right? I mean, so much that, I mean, they're able to feel all kinds of things through this cane. Over time, you also see things like this infamous Oscar Pistorius, who used these blades to run, which moved it away from just a simple fiberglass stick, but something that was high performing. So much that the other runners with feet thought it was an unfair advantage to use this kind of inanimate material, that he can feel and run with these things. So the question ultimately is, I mean, it's not just a matter of low level type of activity for this material, it can actually be at a very high level. And then beyond the material itself is the space around you, right? That understanding of that bubble. And so even as I'm sure any of you who drive, there's a certain understanding outside of your car that you understand what that depth is and how to move your vehicle. Maybe less so now that we have cameras in the car, but prior to the cameras, this is what actually started to, you know, understand that space outside. So can we understand that space outside of architecture as well? Instead, what we have are these boxes, and we design and build these boxes. So to me, again, it's like, why we're, you know what I mean, we're humans, we're bodies, we're animals. You know what I mean, why are we living in boxes? Ultimately, it's the most inorganic shape possible. And my question ultimately is why. In 2008, I found this Gina car by BMW. Is basically made out of Lycra. And what happens is that as the car speeds down the highway, the variation in speed will change its form. You can see here starting to change for different performances. You mean maybe the spoiler will come up. All these things start to conform to its performance. And then on the inside, the seats also conform to the human body. So as you sit on the inside of the car, the seat themselves will hug you and become very tight fitting, like a glove. So ultimately, I thought, well, an architecture should do this too, that it should be responsive to what's going on, and especially the environment that is changing all day long. And if it is, in fact, responding properly, the facade in the outside would be changing depending on where it is in the facade. So higher up in the building, you'd have higher winds, different temperatures. Lower, it may change because of the cloud coverage or trees blocking it. And so the change should actually happen throughout the day. So some others also have been trying to make these things happen. Here you can see by Studio Igni, they made this project that very cool, responds to the body as you move through it. But you can see the problem is all these wires and the electricity and the Arduinos needed to make this happen. So to me is, how can we do this? How can we make things move like this without electricity? At the same time, I became very infatuated by climate change. Elizabeth Colbert wrote this book on catastrophe and climate change and how it was nearing. She started these essays probably in the year 2000, earlier than the publication of the book, that really impacted me quite a bit, trying to think of how we as architects really have to think about how our buildings are going to also adapt. The quick history, as you all know, long ago, our buildings had thick walls and small windows. It worked quite well because they worked as insulators. So when it was cold outside, the inside was warm, and vice versa. And because the windows were so small, there was a lot, or it minimized that kind of heat or cold transfer through those surfaces. Moving forward very fast, we have the invention of plate glass and long-spanning steel. And suddenly that heat could come in very quickly and easily, not only through the material of glass, but also through radiation by the sun just coming through. Therefore, we had to invent air conditioning, and air conditioning over time has grown so tremendously that in order for it to perform efficiently, we have to seal off the building. The building is now a capsule, and most cases cannot open any windows in order for it to perform properly. So this seems to be a problem. High energy, very distant from nature. My idea too, and it goes back to my biology days, is to think about the building skin as human skin, whereas it does many, many different things. One, it's waterproof. It actually protects you from disease. It sweats to cool, goosebumps raise to warm. It does all these different things, and it's the largest organ in the body. And the best thing is it actually reduces the reliance on the heart and the lungs, which is the equivalent of like a mechanical system. I started to then look at smart materials, right? Thinking that if we're going to make something responsive, we have to start with materials that are responsive in itself. So smart materials, different than the use of smart in itself, is actually something that responds to changing conditions in their surroundings. And it requires no energy and no controls. This obviously is very different than what we call like smartphones, which is the absolute opposite. But the engineering term for smart actually is this. And the material that I came upon was thermal bimetal. And thermal bimetal is a material that actually has two different alloys of metal laminated together. And when the temperature goes up, one side expands more than the other. So it has different coefficients of expansion. It will go back and forth millions of times, mainly because they're molecularly bonded together. So what I'm going to do now is I'm going to show you some of the projects that I have done using that material, and then some of my more recent work at the very end. As I told you before, my interest in climate and how architecture needs to respond to different things is actually in different kind of categories of its operation architecturally. So in this case, it's in ventilating surfaces. How do you make surfaces so that hot air can actually escape? And this is the first project in 2009 that we tested the material. The material has never been used in a surface-like condition. And at that time too, I was really consumed with looking at how to make a design from beginning to end using computation, right? So that the computation was part of the fabrication process. So this one actually used a very heavy modeling tool called CATIA, which is the type that eventually became digital projects for Frank Gehry's office. But, you know, it's you know, in 2009, which I don't think of that long ago, it took us, just to give you an idea, about 16 hours to instantiate this model, to actually run the model so that the surface was actually populated by all the different pieces that we wanted. Very slow, very heavy. Anyway, the idea was that as the temperature went up, the basket weave would crimp and allow air to actually pass through. We also eliminated any fasteners, tried to eliminate any kind of structure that would block the access of heat to the surface. And the result you could see is this kind of crimping of that surface as it heats up. And again, it returns when it cools down. So that was a big deal for us because, you know, we actually did not know what we were going to get. It was the first time I ever used the material. But since then have done a lot of different things with different thicknesses of the material itself. Here you can see making an oculus open and close. Using that geometry to expand into a larger surface. So there's multiple openings that open and close. Again, you know, a lot of the intent was trying to make surfaces, because architecture is basically made out of huge surfaces. How do we scale up to the scale of architecture as opposed to always make these things that are really small? So that's something that, you know, working with geometry has actually helped a lot. With that ventilating too, started, again, I'm jumping around with different projects, and these are not necessarily sequential at all. But in this case, did a project for Toyota Prius. They wanted to have something for events at night, which was problematic because I did all the work that actually responded to the sun and was intended to respond to heat. But this responded to theater lights, and you could see that basically the idea was drilling a hole through this whole loaf of thermal bimetal. You can see here in the slow-mo, or sorry, in the still image, the pieces are actually starting to tilt over so that they start to tilt as they start to heat and drill through. We reconfigured it for a different installation, taking all those aligned parallel planes and reconfigured it in a tower. And the nice thing too, is you can see on the bottom right, relative just the sun hitting it, all of a sudden these things would also open up, which I was much more thrilled about than just the theater lights. Eventually, and most recently, this led to a project for Louis Vuitton, which you can see here in a surface that was going to expose a LED screen behind. So as the night came out and the pieces start to rotate, you can see through the system, a LED system for advertising in the evening. Energy generation also was part of what we start to think about, because obviously we're just using the sun one-to-one to make these things happen. In this case, this is a typical ventilator for a rooftop. I'm sure you've all seen. The problem with this ventilator, you can see, is that in the cold times, it's all open, and cold air can actually go down into those spaces and into the building's interior below. In order to prevent that, we started to think about how can we make something that can rotate and activate when it's hot. Again, these pieces get hot, they flip open, they catch the wind, and then when it actually cools down, we'll start to close up and reduce those openings so it could reduce the cold air coming in at the end of the day. So you can see these closing as they go. The other energy generating, you can see here, the heat lamp is acting like the sun. And so if we heat one side of the system, it basically spins forever. And so we can actually start to generate energy. Now, granted, it's very low performing at this point in time, but still a perpetual system. You can see the number of different types that we went through. I have to say on this project, you know, it's funny because I use a lot of students and have a lot of interns in my office. I now remember 2 of the students who worked on this over time are both from Elac. They were Elac transfers. So they were very, very helpful. This then led to and why is this not starting? Let me see here. Oh, this led to me trying to think of how we can make these things rotate. Now, this looks really simple, looks very, very crude. It took us a long time to get to this point because we wanted to make a system that would somersault forward. Then instead of going forward and then backward to its original position, how can we make something that can actually then spin, you know what I mean, again, like that energy generating thing forward, but again, in a modulated way. So it's I know when people see this, like, oh, what's a big deal? It took us weeks to get to this point to try to get these things. So I just show this just to give you an idea of what it is. And then what we do is after that, we try to find the most simple way to move forward. How can we even simplify it even more? Because we want to eliminate any extra parts and any extra things to make it manufacturable as well. What that led to was this installation that we did last summer. for a school in Washington, D.C. As the sun came across, you can see those little pieces in there. It would actually flip and they'd ring the bell or the sphere of the one adjacent to it. So it became a musical instrument and was sounding as it went through the day. Sun shading. This is a project that Ingelo is familiar with because we worked on this together. Basically, at this time, it was in early, or it was in probably 2011 that we worked on this project. Looked at scales of fish and how, this kind of parametric surface can actually be moving across on the surface and differentiated. We ended up building this project called Bloom at the Materials and Application Gallery. At that time, it's about 21 feet tall at its highest point. Used very innovative structural systems, but the idea was basically how can we use that movement to increase shade or increase ventilation too. You can see here, this is when we used both the CATIA model as well as the grasshopper modeling. And at that time, grasshopper was just starting up. So it didn't have a lot of capability. And we didn't have a lot of faith in it either at that time. So that's why we ran the CATIA model in the office. So we had two different competing factions. There was a point in time that we actually flipped over and finally decided to use a grasshopper. We were able to help Grasshopper, the company, develop their product so that it can go from design all the way to fabrication as a result of it. But the idea here, as you can see, I don't know if you see my mouse here, the top portion can actually be very narrow depending on where it was, and then the tail on the bottom side can actually change in length. And what we did was we connected it to different types of analysis models. In this case, it was Ecotech. The areas in red had a lot of sun throughout the day. The areas in blue have no sun. So you can see here that variation was expressed in the surface itself. The tails are very short. You see in the areas that are almost transparent and very long in the areas that actually saw the sun. Through the course of the day, we did not know if it was actually operating until we actually took this time-lapse video. The video, again, is in January because of, here we are, 80 degrees in January, which was perfect. But you can see how it did operate and respond to the sun as the actual shade is coming across. So that was really exciting for us. That was the first outdoor installation that we made. This led to other ideas. I started to look at assembly strategies using this material too. How can we actually consider how it can affect assembly? When designing that project Bloom, we had about 14,000 unique pieces. So here you can see we're trying to find ways to sort them before building them. Then we went to lunch and then we came back and everything was all messed up and we didn't even think about the assembly part. But over time, we realized that assembly was very, very key when you're working with this kind of material. So after 14,000 pieces, I decided that it's like, it's just so hard to keep track of 14,000 pieces. I just want to make a project about one piece and not even worry about that. So that was this project, which you can see, here's the material that comes in these rolls. And I wanted to make a project that basically used the rolls and just wound up on itself. A lot of the projects that I do, I try to eliminate, like I said before, fasteners and try to use more like tab and insert systems together so that assembly is very easy and that it requires no skill and even someone like me can put it together. And start to look at the complexity of what that is. So you can see here the different studies, the different types, how we can use the same forms and pull them far apart, like in this B section, or squeeze them tight together and get D to get that variation. You can see the kind of, even this was hand cut at that time to see the variation you can see in the background of depending on where it is and where it lines up with the other pieces, how complicated these systems can be. The drawings, the sketches that we go through, so that in some places it would have a very long, tab that you see here. In other places, it has to have this hook so that it won't undo and it would hook onto each other. And then even in other places, you see at 9 here, it actually deviated and lopped off. part of that part of deviation is we started to then, because we always like these challenges, make this skeleton system that would be inside and outside. It would actually be an endo-exoskeleton that would rotate and move all the way around. And that number 9 point was where that exoskeleton moved to become an endoskeleton. You can see the different models. I show this just to give you an idea too of how we go about doing this and how the idea comes. The one that started on the left was first, but we made this and it was very, very floppy. We realized we needed structure. We moved to plastics. You can actually see inside. This is a completely internal structure. It worked well. Had trouble seeing it because it was plastic and your eyes just go cross-eyed because you can't see what's going on. So we used the coffee stirrers, the little tape to understand the pattern that's actually coming out of it. And then on the right, obviously, we moved to a combination of clear plastic and opaque so that we could see a little more. Another model you can see here is testing the assembly process. You can see on the bottom left-hand corner, we assembled it straight. It was pretty easy with 2 people before we close it up and whip it basically around again. The final thing was this. It actually has a heating element in the middle so that you can see these longer pieces in the middle were intended to actually flare and close up the center circle as it went through. Looked at also structural surfaces, how the bimetal can actually help with structure. In this case, making a pre-stressed surface. You saw that video on the left, or when it gets hot, we insert the piece, it cools down and makes like a bow and arrow. In this case, the material that we use is much thicker. It's very difficult to bend mechanically or manually. And so is the heat at about 300 degrees that actually helps us make this. It basically is a one-hand, one-person installation. You could see the gloved hand. You do need a glove because it's hot. Inserting it there, and as it cools, it then fixes into position and ready for the next one to be installed. You can see on the left, the person in the middle, the silver pieces are the bimetal, the colored pieces are aluminum. That oven you can see in the distant back is where we heated the pieces and brought them back and forth to the person in the middle. Assembled it probably in about 6 hours. You can see in the video on the right, the floppy pieces of aluminum start to stiffen up nicely as we finish putting in the last pieces of bimetal in the middle. In this case, we finished it, but like we make mistakes on every one of our installations. The mistake we made here is we didn't think about how to get the person out of the middle once we finished. So that was a little bit problematic, but we ended up using a lot of the pulleys to pulley him out. We got him out. We built the bottom of a 5-tier tower. We're in the process of actually making the upper tiers as we go forward. Use that same technology and the same idea to make a surface that was 3-way instead of 2-way like that previous one. Looked at nature as we always do for that inspiration of how and what we build. You can see here in this diagram, the blue is the cool pieces. As it heats up into this pink and red, they reconfigure so that then we position it in its final place and its position. We go through a lot of different study models, as I mentioned before. This one I tried to show in scale relative to each other. The little paper models are about 6 inches diameter. The big silver models are actually to scale are about 3-foot diameter. So we went through all different variations of it before we landed on this one here. It's about a 9-foot diameter sphere in the end. The petals, some people ask me, oh, wait, where'd you get your aesthetics? And, it's so feminine looking, which I thought, I actually found a little offensive because it was not meant necessarily to do that, although it might. But like in nature, the petals in this case were designed to hook onto each other so that the thing basically would not explode. So they're actually completely functional. And the colored items, again, to differentiate in this case, were also aluminum, whereas the silvery pieces are made out of thermal bimetal. You can see here structurally, We put it together. Again, the idea is that there's no fasteners, that is just all pre-stressed surface. You can see that it gets really floppy until that last piece goes in, but that's just, again, the physics of making a sphere. It became very stiff at the end, you see. So its final resting space is at the South Coast Botanical Garden. If you want, you can actually go check it out there. This led to self-assembly. So the last one was a one-hand, one-person assembly system. This is 0 people, 0 tools, 0 hands, right? Again, it's very, very simple. We made these very tiny little installations using heat to assemble itself. It's fun. We get a lot of calls about this. I haven't developed it that much further, except that right now we're trying to make this flat pack self-assembling toy vehicle. This is a wheel as part of it. You can see it actually goes into the bubble. We've made boxes. We've made some other shapes too that work. Now I'm going to talk about the window system. I show this because, again, my intent as an architect is try to get all this to market somehow, to try to change architecture, as I mentioned before. And so this is the closest way that we've gotten, and which is really quite exciting. Just to talk about it a little, just to review, you all know about energy problem. Buildings, you can see here, use up about 40% of all energy in the US, 40%, more than transportation and industry. And within the building, the HVAC system, right, the heating, ventilating, air conditioning system uses up about 45%. So because of the energy uses, I tried to think of ways to reduce that energy. If we could bring it down 1%, 5%, anything, that would be huge relative to energy use, considering how much is used across the US. Air conditioning is a problem because with the heat island effect, which I think you all know about too, as cities get hotter and hotter, people use more and more air conditioning. And in order for air conditioning to work, in order to cool the interiors of buildings, it has to expel hot air into the atmosphere. So the hotter it gets in these cities, the more air conditioning is contributing to the problem. So how do we get out of this and not contribute to that heat island effect? Just to give you an idea of energy use too, 12% of all energy in the US is used for air conditioning alone. That's not even including heating, right? So you can see in both the commercial sector as well as the residential, although it's differentiated, it is a problem, all around. So here's the windows that everybody likes. Everybody wants that beautiful view across the US, across the, 360 degree if you can have it. Floor to ceiling. But the reality is, as you know, without coatings, it's going to be a lot of heat gain coming in. With low E coatings, you can control that heat gain. But the problem ultimately is a wellness issue. It's like wearing dark sunglasses all day long. So that's what they're learning from this. It's cheap, it works, but it's not really what you think. Electrochromic glass, where you can control it, requires a lot of electricity and wiring for you to be able to turn that on and off. It's very, very expensive and oftentimes has a color tone to it. Heat gain, we still have with blinds, right? You could, once the heat comes in, the blinds actually don't help at all. What it does is it helps with glare, not with heat gain. And obviously what it does, it constricts the view in any case. And oftentimes people don't control them regularly. They have to be automated. So the windows that I designed is put into the cavity of a standard IGU or standard double glazed window system. You can see here, as the sun hits the surface, it actually flips over. The good thing is that when it's in neutral position or in active position, you don't lose visibility whatsoever. It just works by itself. So you can see here it is up close. These are the little bimetal petals that flip over when the sun hits it. They do so very independently and don't require any energy to do so. We have some installations here in Hawthorne, California. Another one we just removed actually just a couple weeks ago from Long Beach campus. You can see the pieces flipping over from the outside on the left, and then on the inside, the shading that it actually provides throughout the day. So it's exciting because this material now is commercially available. We have a lot of recognition, all kinds of things, including the Cooper Hewitt National Design Award. The last thing I'm going to show now is just stuff on public health that I've been working on more recently. It's stuff that's not using bimetal, but something that I feel can make even bigger and greater impact in architecture. The idea that I have is here's, again, the crude section of a city where you just have a lot of buildings. My proposal is, why can't we use all these surfaces, not just the ground surfaces, for infrastructure? These surfaces can actually be used more for the public good, including public health, for public reasons. And the better and more we improve these surfaces, the better our cities will ultimately be. There'll be enjoyable places to be in outdoor spaces, and not people racing in to get into those indoor spaces. So one of the projects we're working on with a big team of experts is smog eating panels, mainly because a lot of the pedestrians are the ones who are waiting outside breathing this type of air. And how can we reduce lung disease in basically the urban poor? Using passive systems too, because again, I'm not interested in using a lot of electricity. I'm not interested in cleaning, 100% the smog, but how can we do this passively? And we do a lot of things passively, things will still get better. But using little chimney effect, using primary sources of wind, using plunger effect from buses and stuff running through urban canyons, we're able to move air through these little tubes. And so you can see here, we're starting to develop some of those surfaces, working with aerospace engineers. I just have to say too, these, I was nervous about approaching aerospace engineers because at first I thought, oh, well, we just have to use civil engineers. The problem with civil engineering I found is they pretty regularly don't think out of the box of what basic structure is, especially for architecture. So when I approached these aerospace engineers, they thought this was the most radical project that they ever saw in their life, because they typically work with wind speeds that are like Mach speeds for airplanes, right? And so they were super excited that this airflow was so slow that, they can possibly do something to control wind speeds. So it was actually really quite exciting. We are continue working with them. You can see some of the development, some of the tubes and how we're moving through them. We're now looking at the filtration system of carbon, of titanium dioxide, of all types of things to be able to 3D print and thinking about 3D printing to be done in any country, anywhere in this world, so that it becomes a little more open source, and using local materials as a way to do it. The goal is to eventually design some architectural panels in a rain screen type of situation to filter that air, and also a bus shelter system, right? So that the people who are waiting for buses, who end up breathing some of the worst smog, actually have the freshest air in the city. So we're now trying to work with automobile companies so that they can actually do the funding for these types of shelters too. The last thing I'll show you is some of the stuff that came out of the robotics that we do. Here you can see very fun little robots that we make in my office. We did these for fun. I never thought these would amount to anything. But as we start to make these things, and this one kind of rolls, we started to name them. They bring joy to our life. They roll, they scooch, they hop, they do all different types of things. And our interns, I started doing this as an exercise for interns, as a way for them to start to understand the material, but have amassed a collection of them that are super fun. And I never thought that it would actually influence architecture, but I noticed that everybody always smiles when they see it. So then I thought, well, if that's the case, why can't we make architecture that will make people smile, right? And the idea was that basically what we can do is, if we make one person smile, 100, 1,000, 10,000 a day, we can actually improve the mental health of a city, right? Just a tiny bit. Again, we're not saying it's all better, but even if we can make 2 seconds better for everyone, there's a lot of studies that show that the endorphins increase happiness for people. So started to look at that, work with interns again, thinking about what is going to make people happy, starting to work with psychologists and sociologists of how that can actually work. Did some crude different things that actually actually smiled at you, but start to learn that it's probably not the smile itself that actually is going to make someone smile. Because if you think about it, you won't smile at a video of someone, smiling at you. We're starting to learn that it's actually the movement system itself that's quirky. And the best thing about it for me is that it's the imperfect movement that is making people smile or laugh, as opposed to the perfect movement, right? So instead of being perfectly engineered and everything's lined up perfectly, it's those inaccurate moments that actually do it. So we're really good at those inaccurate moments and not making them line up. But anyway, I end on this Blade Man just because I'm so interested, I think, as I mentioned before, in the biology. These are skeletons. The man has no skin. There are so many things that seem to be wrong about this photo, but at the same time, we're completely infatuated with. So I'd like to end on that. Thank you very much for listening to my lecture. I'll stop sharing now. Thank you.
Yay. Okay. At this point, we always end up with question part of our lectures. And I'm opening the microphone to our attendees.
I see
If
Anthony
anybody
has,
has
Anthony has his hand up. Yeah.
Yes, okay. Or you can also type your question in the chat section if you don't have a microphone or anything like that, and we'll voice it. Okay.
Hello, thank you for being with us, Ms. Sung. I have two questions. So the first one is, speaking about the thermal bimetal in architecture, it seems that it is ostensibly used as a facade currently. Could you use other forces that create thermal energy that would allow this material to be used as a structural component that adjusts to stress when needed?
Yeah, so the projects that I showed, that there was that kind of tower project. The idea to that is to try to make something actually as strong, a structural component itself. So it's actually performs as a column. It's very lightweight, it's extremely strong. We work with Arab Engineering on that project. And it was so complex that it actually at that time crashed their computer model, and they could not analyze it computationally. They said that in order for us to test it, we actually had to load it the old-fashioned way by putting sandbags on it. But the problem was that because it was sponsored by a fabricator, they agreed to doing the fabrication for free if they could keep the piece in the end. And so they did not want to load it in the end. But it's also funny that you say that, because we also have done, we've done a whole bunch of different projects. One of them was for New Balance shoes. And what we designed was this kind of arch support that went in the shoe, so that the hotter it came, it actually increased the arch support, which is the opposite of what most foams actually do. So as you know, I'm sure you all have worn tennis shoes or sneakers, that over time that insert of foam actually compresses and does not bounce back. So that in a way is its own structural system in an arch that would increase with heat.
Thank you. My second question is, I plan to apply for the undergrad architecture program at USC this coming winter. And I'm just wondering, what can I do to increase my chances of getting accepted?
I think the best thing is to work on your portfolio. The portfolio is actually very key. We do offer a few portfolio sessions that you should try to attend. They are typically online. My associate director actually runs them, Lee Olvera. He answers a lot of questions at that time. So if you have any specific things, those are the times you should bring them up, and you can actually show him even parts of your portfolio. Keep in mind, though, that, I think the things that they look for are two things in a portfolio, especially from transfer students. It's not only a sensibility for design, but to see what the skill set is too. And just to give you an idea, right now in our first year, we teach Rhino a lot in the first semester, and we're actually starting to teach Grasshopper in the second semester. So if you have opportunities now or in the fall to learn Grasshopper, this would be a great time to do it, is what I would advise. But I mean, don't be as, I don't think you have to be as concerned about the architectural components. Like, we're not looking for portfolios that have a lot of architecture in it, but a sensibility of a person who knows, who is skillful possibly, and has an understanding of three-dimensional space and form. Sometimes in the, the more abstract it is, it might actually be better, and less about plans and sections and elevations, actually.
Thank you so much. This was fascinating. Appreciate it.
We have another hands up, Jasper Elijah Morales, please.
Hi, how you doing, Professor? Pleasure to meet you. I first wanted to compliment what you designed. It gives me Theo Jansen vibes, except with metal and heat gain. So I think that's clearly amazing. But on that note, you mentioned that there's manufacturers that are already catching on to this. Do you see any optimism with the construction industry and with your collaboration with them? Do you see something in the near future that they will be implementing globally?
So the windows are commercially available now. So they're gonna, there's plans for it to go into the University of Florida School of Architecture, brand new building next year, as well as the new Burbank Airport, actually up in Burbank. I guess on a greater level, I don't know if this is part of your question too, is having gone through this entire process, from a startup company, from designing these things to a startup company. And again, previously, for about 17 years, I practiced as an architect too, just a conventional architecture. I've learned that, all architects actually design products too, furniture, jewelry, building systems. But architects don't think in entrepreneurial ways is what I find is problematic. And so therefore, a lot of firms are not diversified. They're just client-based. So if the economy goes bad, everyone gets laid off, but jobs disappear, work dries up. Why? And so as a result, I actually started a new 4-year degree at the School of Architecture at USC. That is specifically around product design and entrepreneurial thinking. So that degree is a Bachelor of Science in Architecture and Inventive Technologies. It is not a professional degree for BArch students. We still have that. So we have a track of students who want to become architects, and then we have a track for students who want to design architectural products and be entrepreneurs, bring things to market like I did. That program we just launched is starting with its first incoming class this fall. So we're super excited about it. It's a completely different way of thinking. We have architecture firms, manufacturers, different companies like Nike and Apple already contacting us because they want to hire our graduates. And I keep telling them, it's like, we're not going to have graduates for 4 years, but it's actually a very, very positive thing. We actually have a lot of people who are knocking on the door to also teach in our program, even though our program's not obviously growing that big. So it's quite exciting because I think a lot of students like yourself and others are very interested in this type of area. And so it's a response to doing some of that, what is considered market research, or talking and understanding what's out there. So that's something to look at as well.
We have another question, Marisol Vidal. She's asking, I just want to start off by saying that this was truly inspiring. It's been a while since I was truly excited by a speaker. So thank you for that. I'm not crazy about the shiny metal, but the functionality is awesome. can anything be done to change the colors? I saw the blue and that was nice, but I know a lot of people are comfortable in their bland beige boxes. How long do you think it will be before this becomes industry standards? Do you come across people saying no to this biomimicry, or do you find that more people are saying yes?
Okay, so there's multiple questions there, I guess, right? The color, the metal is like any metal, so it can be painted or coated or treated, just like any metal. And it actually has to be, if it's put on the outside, exterior condition, because it'll corrode like all other metals too. And obviously you can do any color that you want. So I guess that is kind of the color question. The other question, I think, is there any pushback to this material? Do people not like it, I think, if I understand the question correctly? It kind of goes both ways. There's a whole conservative attitude that, in the industry of they don't like new things, because of course, the questions that we always have is maintenance issues. Like, is this going to be really hard to maintain? Are we going to have to, repaint it every few years? Well, yeah, because actually in architecture, all materials have to be maintained, right? Like your house has to be painted every, 20 years or whatever. So like anything, yes, it is true. But the maintenance is not a daily maintenance unless, you want to, put it on the outside in very dirty areas, for example. The other questions I get is like durability. How long will this last for? Will it go forever? And virtually yes, because it is actually material that I mentioned before is molecularly bonded together. It's actually crushed. There's no adhesive between it that can fail. It will not delaminate and will not change over time. It will lose its capability if just exposed to the elements without treating of some sort. Other than that, I think most people in the building industry, and this is kind of the sad thing about our industry, are adverse to new things in general. If you can imagine, put it this way, when people design their house or they want a house, what they're looking for is nostalgia, right? They want a house that's either a bungalow style or they want a Tudor style house, or, I want it colonial style. And it's very, very different when they choose a car. The same people will choose a car for performance. They'll choose it for, gas efficiency or for electricity, it's an electric car or all these different things, despite the look of it, right? So every 5 years, someone can buy a car. It's like completely different. And, very few look like the Model T or, something that's very, very old. So why is this true? When you buy a house, you're not looking for the most state-of-the-art thing, because the state-of-the-art house today would not look like a Tudor style house. That would not look like a wood timber, system. So why? And this is questions that you all have to, think for yourself, is how much is it? Now, there's that nostalgia of memory and all those things that probably do play a role in it, but why doesn't it do that for an automobile? And ultimately, you just take that and you scale it up even further. A developer wants to sell square footage or lease square footage. They want to go with the safest thing possible. They don't want to go for, newfangled, crazy looking, thing. They want to stick with the same old thing. And guess what? Manufacturers want to do that too. So manufacturers make a lot of money on the things that they make, whether it's window systems or concrete or cement panels or whatever. And they are very, very successful at that. What they're scared of is things changing, because that would cost them a lot to change their manufacturing process, and they don't want competition. So I've also found that, there's companies that want to buy us out, mainly to shut us down, right? So that we stop competition. So it's a very unfortunate industry that you would see architecture still being built exactly the same way it was built 100 years ago. And given climate change, given new materials out there, given technology that's coming about. The only thing that we describe a smart building or a smart house is by the number of gadgets that are attached to it. Just because it has a smart doorbell, just because it has a smart thermostat, you know what I mean, all these little gadgets. But if you look at the floor, the ceiling, the walls, they're exactly the same. Why?
We'll take one more question, if you would, Doris. It's Christian Torres, please.
Hello. Hi, my
Hi.
name is Christian Torres. Nice to meet you, Doris.
Nice to meet you.
I really enjoyed your presentation. Specifically, this semester we're tasked to design a shade structure for Joshua Tree. And it's really hot in Joshua Tree. And I was inspired by the Serpentine Pavilion, but we also had to study an animal. So an animal that I got was a desert spiny lizard, which has adaptive scales. And so, which led me to kind of try to think of a material that adapts to the heat, just like the lizard scales. And you kind of just nailed it. And so, yeah, I really am impressed, and I'm trying to absorb as much information as possible. But I do have some questions, like with the adaptive scales that you have that allow for better ventilation. Is there like I have a number of questions, 3 questions specifically. First question is, how do you decide what shape these scales make to allow for better ventilation? Do you choose curves? Would it be more functional to have certain angles, straight edges, or round shapes more optimal for airflow?
So this first question is, how do we choose the shape basically for a lot of these things?
Yes.
I guess, Christian, what we do is we start with the simplest form possible, right? Because to me, it's like, we don't worry about the form until much, much later. We have to worry most about performance. We have to make the thing work. And why can't we just start with a simple strip first? And so that's where we start. As we start to move forward, and we have to figure out how to connect it to something else. And you know, I mean, there's so many variables designing these things that you just don't think about that then alter the actual shape of it. Even in the end. So for example, on the Bloom project, one of the people who was working the model really liked the sharp corners on it. Like there's all these sharp corners. And I said, well, no, we can't have sharp corners, right? Because people are just going to get, you know, scraped and caught, you know, on their clothes and stuff. And we argued and argued and argued because I just said that the function of that was that it was actually kind of dangerous, so that it could impale people. And we came up with a, you know, I mean, a way to basically fillet the corners of the pieces, or to round the corners so that they would be acceptable in the end. And we thank God I had the I told you so moment, because when we were installing it, and like I told you before, you know, we start in the morning and all the pieces are flat, but in the middle of the day, these pieces would start to curl. And when we're installing, they're all curling all over the place. And, you know, I mean, as you're holding and stuff, there's pieces that are scratching your arms and legs and everything. But thank God we filleted those corners, because I think there would be a lot more blood in the installation process if we didn't. So everything, all those little things actually play a part in the actual shape in the end, and how we connect to each other. How do we, and the final question that we go through on our mind too is that, you know, what is the simplest shape we can make it? Like, these don't have to be complex shaped pieces. And so the more complicated it is, the more weird and unpredictable the pieces will operate in. So if you see, a lot of our pieces are very, very simple. And a lot of people think, oh, it's probably, you know what I mean? How, you know, it probably didn't take that long to get to that simple shape. Well, no, it took, it did, you know, and that's why I tried to show some of the things that we did early. But, you know, I have hundreds of slides to show you how many shapes we went through for that window system alone, right? That in the end turned out to be an elliptical shape.
I really like that window system too. The blinds, the self-functioning blinds.
Thank you.
And know if you have time for 2 more questions, but
Sure.
okay.
Christian,
Oh.
can you just keep it simple? There are other people who wants to ask
Roger,
questions.
right? Yeah. Sorry. Okay. Last question. So the biometal is made out of metal. So my last question is, or the more important question out of the 2 is, how bad is or how well does the metal function when absorbing heat? So the metal is obviously going to absorb a lot of heat and absorb a lot of that radiation and probably diffuse the spaces inside. Are the biometals, do they have an extra function that reduces that radiation so that way the spaces inside don't absorb the heat from the metal?
So the metal that we use, especially inside the window system, is so thin, it is like just a kind of thick foil. So the heat gain that comes from that transfer is not a lot, because the mass itself is very, very small, extremely, extremely lightweight. They're so thin that, again, we have to seal it inside the glass, because if you touched it, you can actually crimp it very easily. Just to give you an idea, if these pieces were like the hood of your car, like the thickness of the hood of your car, which the structural pieces are, that absorbs a lot more heat, so that over time, in the sun, you can actually feel it, and there's heat absorbed into the material. But the thin stuff, no matter how long and how hot you heat it, will never burn your finger or anything, even if I were holding it.
So when you were making that column, oh, sorry, I'm so sorry.
We're going to take one more question from, I spoke too
Thank
soon
you.
before.
I appreciate it.
From Myra.
Hi, thank you, Orhan, and thank you, ma'am, for being here. It's really exciting what you're doing. Like another student said, it's been a while since, you get excited about new things going on. But I think, Christian answered the question already. I was wondering about the heat release and how, if you guys were finding a way to store that and actually make it useful. But like you said, there's not a lot of heat being absorbed there.
But I guess it can be, though. I mean, that's a great idea. I haven't thought of that yet, of trying to grab the heat and store it. It's, it's funny because it goes along the lines that a lot of people ask me, it's like, well, why don't you start to work on other materials, or why do you do all this stuff with just bimetals? Because like what you say is, every time I finish something, there's like, 10 more ideas of what to do. That is like, okay, well, I'll just finish these and then we'll move on to another material. But each time there's like more and more and more. So the job is just never finished is the problem. But that's a good idea. And another thing that we're working on is very similar, is trying to use it as a reflector. So how to get that sun to, that by the curl and the shape of it, can we actually reflect the heat so that it actually heats something else? And so that's something that we have been working on.
Yeah, and I thought about that because, heat, there are some products that change with heat. So the color changes, and I know somebody had a question about color. So that's probably something,
that's true.
Could be done.
That's true, like a mood ring.
Exactly, yeah.
Well, thank you for great questions, Elac students. We are really proud of you, that your attention and your curiosity to this, as they say, the curiosity is the biggest drive in architecture. And we are so grateful to you, Doris. And I know doing these things for a long time, lecture series, that I know when the students are inspired, and you really inspired everybody today. And maybe they change their mind to how to go about architectural degree and take advantage of the programs that you are doing at USC. So thank you so much for having a time to talk to us.
Yeah, no, thank you very much. And please do apply, anyone who's interested or ready, because we do take a lot of transfers from Elac. We love them. I have to say, and I told Ingela this before, is some of our Elac transfers are some of our top students who graduate. I have to say, like I said, many have worked in my office even, and I'm pretty indiscriminatory as to who I hire. It just so happens that they went through Elac and transferred, and I thought that was really quite interesting and exciting. Very different backgrounds, very different interests.
Yeah, and can I also, with this new program that you mentioned, Doris, just reminding everyone that in California, you do not need a NAB accredited degree to become a licensed architect. So that's a different pathway that you, if you're interested in the work that Doris is doing, you can get a 4-year degree and still become an architect in California and 16 other states in the United States. So just saying.
And probably have a great chance to go to graduate school after that degree. They would just really want you to go to their school if you have that particular degree, especially.
And workforce, I bet you.
And you know what's really funny, and I'll just share this with you because this is just it's a new thing that I learned, is that we have a couple students who figured out the system. They basically did the 4-year degree at our school. Were able to get a scholarship to go to the school, came up with portfolios that were great, now are going to go to graduate school at Harvard and Columbia with a full free ride, which I thought, wow, that's like brilliant, right? So I never thought, thought that way before, but they figured out the system. So anyway, you never know. You never
Speaking
know.
as a mom with 3 kids in
Yeah, I wish one of
school.
my kids thought that, but
Similar thing happens with landscape architecture degree where I used to teach at Cal Poly. And 4-year degree, landscape architecture, wonderful degree for graduates programs. So you have
Yeah.
choices.
Yeah.
People.
choices. Anyway, thank you very much.
Thank you, Doris.
Enjoy your weekend. I'll see you soon, Ingelo. Thank you, Arhan. Thank you, Gilbert. And I hope to see you all soon.